The program starts by setting up the Arduino controller. This is where the loop starts. The sensor in the circuit is used to detect the battery pack's temperature, and the reading is displayed on the LCD. Now, we move on to checking the temperature conditions. The condition used here is, when the temperature exceeds the maximum temperature, a high temperature warning is activated to ensure the user's safety. And conversely, if the temperature does not exceed the maximum temperature, the fan will be switched off. Once the warning is activated, the cooling system will also be activated, and the cooling fan will be left on. After some time, the cooling fan will switch off. Now, is the current temperature lesser than the maximum temperature? If it is not, the entire process will be repeated, and if yes, proceed to checking the PIR sensor. The PIR sensor is read to detect any motions, and for instance, we can detect heat energy in the surroundings.
Hi, my name is Ain and I will next present about the coding part. So for the first line of the code, which is #include liquid crystal 12C, this line actually includes the header file for the liquid crystal library with 12C support, and this library is commonly used to interface with the character LCD displays over 12C. Next is include wire.h. This line includes the header file for the wire library, which is used for 12C of communication on Arduino board. Next, for the fourth line of the code, which is the third group of the code, is where we declare a constant, which is like, for example, for the first line, constant integer buzzer equal to 7. This line declares a constant integer variable named buzzer, and we assign pin 7 to it. Same with the other constant, which is constant float max temperature, which we assign to 50 degrees. Next, the next group of code, which the void setup. This is the setup function in Arduino, which runs when the microcontroller starts. Inside this function, the pin modes for the various components are initialized, where, for example, for the first line, pin mode PIR pin input, which is for this code, we set pin PIR pin as an input likely to read data from the PIR motion sensor. And for the last group of code, which is LCD begin 16,2, where we initialize the LCD display with 16 columns and 2 rows. Next, LCD in IT, this line initialize the LCD module, and the third line, which we turn on the backlight on the LCD, and the last line indicates that we clear the LCD base. The first line of the code is void loop. This marks beginning of the loop function in Arduino. Code inside this function runs repeatedly after the setup function is executed. The second line is integer sensor value, which is equal to analog read A0. This is presumably connected to a temperature sensor, and the analog function reads the voltage at the specified analog input pin and convert it to a digital value between 0 and 1023. Float temperature. In this line of code, we calculate the temperature in degrees Celsius based on the sensor value. It assumes a linear relationship between the sensor output and temperature and applies a conversion formula. We then convert the sensor value to voltage, which we assume 5-volt reference voltage and 10-bit resolutions. Next, LCD set cursor 00. This line indicate which is print the string temperature on the LCD starting from the current cursor position. Second line is temperature, which this line print the string temperature on the LCD. Next is LCD set cursor 81, which we set the cursor position on the LCD to the ninth column of the second row, and LCD print temperature, which we print the calculated temperature value on the LCD. Next, the next line print the unit C for Celsius on the LCD. Delay 3000, At a delay 3000 milliseconds, we also in 3 seconds, it pauses the execution on the program for this duration, allowing time for the user to read the display temperature. And the last one is LCD clear, which this line clear the LCD displays, preparing it for the next iteration of the loop where a new temperature reading will be displayed. For this part of coding, we use if and else if statement. This conditional statement handle different scenarios based on the temperature reading. If the temperature exceeds the maximum allowed value, a warning is displayed, a cooling mechanism are activated, and the system switches to a backup power supply if necessary. If the temperature is below the maximum allowed value, the warning is cleared, cooling mechanisms are turned off, and the system switches back to the main power supply. So, like for the first line of the code, we use if temperature bigger than max temperature. This condition checks if the current temperature is greater than the maximum allowed temperature, which is max temperature. If the condition is true, it means that the temperature has exceeded the maximum allowed value and the following action are executed. Like I've said before, a warning is displayed, cooling mechanism are activated, and the system switches to a backup power supply if necessary. Next, we use else if, which is when temperature is less than max temperature. This condition checks if the current temperature is less than the maximum is below allowed temperature. If this condition is true, it means that the temperature is below the maximum allowed value and the following actions are executed, as I said before. For the last part of coding is where we essentially checks if the PIR sensor detects motion. If motion is detected, it briefly turns on an indicator LED and switches power sources using a relay. And these sequences of action is the part of our security system or some other application where motion detection triggers certain responses, such as activating backup power and signaling an alarm.
Hello, I'm Hazura. Now it is my turn to continue this presentation with simulation of our circuit. Our circuit has formed with combination of components, which is the Arduino Uno, the breadboard, I2C LCD, a TMP36 temperature sensor, a buzzer, PIR sensor, a relay, a bulb, and also a 9-volt battery pack. So, when we complete the connection of the circuit, the first one we can see that the temperature sensor would send a signal to Arduino to display the current temperature on the LCD. The default value shown is 25.2 degrees Celsius, which is considered acceptable temperature for the working environment of the vehicle, as it is within the maximum allowed temperature. Next, we make a slight adjustment at the temperature, which is now 62.56 degrees Celsius. Now, the temperature have exceeded the maximum allowed temperature, which is over 50 degrees Celsius. The system activates a high temperature warning at the display on the LCD. So now the cooling system is activated. It was alerted by a buzzer and a DC motor to represent the fan, which turns as a cooling system in the vehicle. As the temperature high, the faster motor spin, which is act as the cooling fan. After that, system also check for the motion using PIR sensor. If correction detected, it will light up a bulb and at this point switches the relay to the battery pack momentarily before switching back to the main volt supply. The relay controls used to switch the power source, connecting either battery pack or the main power source depending on the inertia properties.
The key aspect of the project focusing on the C++ programming and hardware interfacing inside. First, C++ programming skill. Students will apply their C++ programming skill to develop the firmware of the Arduino controller. This involves writing efficient and well-commented code to manage various aspects of the EV battery thermal management system. They will utilize concepts such as data types, control, structure, functions, and libraries to implement the desired functionalities, such as reading sensor data, controlling the blower fan, and displaying the temperature feedback. The second key aspect is hardware interfacing. Understanding hardware interface is essential for this project. Students will learn how to interface sensors such as the pressure sensors and actuators such as the blower fan with the Arduino microcontroller. They will gain hands-on experience in connecting and configuring hardware components including analog and digital sensors and PWM controlled devices like the fan. Through this process, students will understand concepts like voltage level, analog to digital conversion, digital input, output, and pulse width modulation (PWM). The third key aspect is sensor data reading. One of the primary tasks involves reading data from sensors, such as temperature sensors, to monitor the battery pack temperature. Students will learn how to interface these sensors, read analog or digital signals, and convert them into meaningful temperature values. They will implement algorithms to process sensor data, including calibration, filtering, and error handling to ensure accurate temperature measurement. The next key aspect is output control. Controlling the blower fan for cooling purposes is a critical aspect of the project. Students will implement logic to control the fan speed based on the battery pack temperature. They will utilize PWM signals to adjust the fan speed dynamically, ensuring efficient cooling while minimizing power consumption. Safety features such as high temperature warnings will also involve output control, where students will activate visual alerts when the temperature exceeds a predefined threshold. The next key aspect is user interface communication. Providing user feedback is essential for system interaction. Students will implement mechanisms to communicate system status and temperature readings to the user interface. This may involve displaying temperature values on an LCD screen or using LED indicators to convey system status, such as light bulb. Students will design user-friendly interfaces that enables users to monitor the battery pack temperature and system status effectively. The last key aspect is integration and testing. Integrating various hardware components and software modules is crucial for the project's success. Students will conduct thorough testing to ensure the system functions as intended under different operating conditions. They will troubleshoot hardware and software issues, debug code, and optimize performance to achieve reliable operation. Testing will involve simulating different scenarios such as varying temperature conditions and triggering safety mechanisms such as collision detection to validate the system functionality and robustness.